Ma'am, please start.
Okay. So good afternoon, everyone, to the weekly online lecture series on
Can you
atmospheric.
switch on your video? Can you switch on your video, Dr. Rohini?
So good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly hosted by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University. Today, we will have again the lecture delivered by Dr. Somenath Dutta sir from IMD Kolkata. And he will be delivering the lecture on definition and characterization of hydrodynamic instability in Brunt Vaisala instability. But before he delivers his lecture, I would request Professor Tohida Rashid, founding life member of SAMA, Bangladesh, member of the advisory panel of the lecture series on education and outreach committee of SAMA, and founding chairperson, Department of Meteorology, University of Dhaka, Bangladesh, to please deliver the welcome address. Ma'am, the floor is yours.
Thank you. So good afternoon, everyone. Being founding member of SAMA, I'm one of the hosts. So as host, it's my great honor and privilege to welcome you all to today's online lecture series. I extend a warm welcome to all those who gathered today's lecture session, including participants. I heard from Professor Das that huge participants have registered from more than 50 countries. So for this lecture series, and the number is increasing. So I must say it's a great success of SAMA. So, and dear esteemed speaker and organizer, it's my pleasure to welcome Dr. Somenath Dutta. He's a scientist at IMG Kolkata, India, who is going to deliver today's lecture. I'm hopeful that your vast knowledge and experience will enrich our participants. Thanks for being with us. I'd like to convey my sincere gratitude to Professor Das, Secretary of SAMA, and Professor Ajit Tyagi, President SAMA, and all members who are involved with organizing this online lecture series on atmospheric dynamics and its application in climate science, which is a very important topic for meteorologists and climate scientists as well. So, and I'd like to convey my heartiest thanks to session moderator, Dr. Rahini, I think, and question answer session moderators for conducting the event. I convey my thanks to Mr. Zadav, who will deliver vote of thanks at the end of this session, I think. So from my side, let's make this lecture a memorable one, and we hope the students enjoy this session. So let's start the session. Thank you all.
Thank you very much, ma'am. Now I request sir to please, he can share his screen and deliver the lecture. Thank you, sir.
Shall I start now?
Yes, yes.
First of all, I wish to express my sincere thanks to SAMA and Professor Tyagi, Professor Das, Rohini Madam, Professor Tohida for nice welcome. So now I am sharing my screen.
Dr. Datta, maybe in first 2-3 minutes you can summarize your last 3 lectures, right? That will be
Pardon,
fine.
sir?
In your first 3-4 minutes, you can just orally summarize your last.
Yes. Before that. Correct. Yeah. Actually, today I am going to discuss about hydrodynamic instability because we all know very well that if there is no instability, then there will be no weather. If we have only the mean flow, then we may not have any weather. So whatever weather we are getting, this is due to some instability. So now, so therefore, if we want efficient, effective weather forecasting, and then I think it is better, it is also required to know what are the different the factor, different instability which causes such instability actually. And for that actually we must know that under what condition a means flow will be stable or unstable, that is also required. And also we will be able to know that we will be able to know that what are the different types of instabilities are there. We will also see different types of instabilities are there, and for different types of instabilities what are the criteria are there, and we will see also some typical examples also. Even not only that, we will also see that that instability as such, instability itself does not have any energy. So when any instability, generally instability enters in a family means I mean to say wind flow, then it enters as a small perturbation only. So then what happened, that perturbation by some way, maybe due to the leakage in the system of the main flow, it gets energy sometimes, not always, and it gets amplified and it gives weather to the etc. And in some condition, perturbations are being killed immediately. So accordingly, we define like this actually. So these are the things only we are going to discuss. So entire instability, I think for that actually 2 lectures are there. Today, some part, next class, some parts are there. So now can I start?
Yeah.
Yes, sir.
So you have to excuse me, sir, because I am not able to take a class using PPT. So I will be using the board. Achha, this whiteboard is visible to everyone?
Yes, we can see.
Fine. So the first point is when a zonal wind flow is said to be hydrodynamically unstable. Its typical definition is like this. There is a zonal mean flow field. In this zonal mean flow field, we will first introduce a small perturbations. And then we will see whether that perturbation grows with time or decays with time, or doesn't grow, doesn't decay. If it grows with time, then we will say that that zonal mean flow field is hydrodynamically unstable, and if it decays, then we will say that particular zonal mean flow field is hydrodynamically stable, and if it neither grows nor dies, then it is it is neutral. So this is the definition of hydrodynamic instability. A typical definition is there. A mean flow field is said to be hydrodynamically unstable if a small perturbation introduced in it grows spontaneously by extracting energy from the mean flow, then it is called a hydrodynamically unstable. So now we have seen that while defining hydrodynamic instability, we have mentioned 2 important things. One is mean flow. And another one is a perturbation. Another one is a perturbation. So now there are some, one is mean flow. There are some some instability. And now when I say, hello, shall I continue?
Yeah.
Now, whenever I say mean flow means what is the speed of the mean flow, velocity of the mean flow, what is the share of the mean flow, vertical share or horizontal share, etc., etc., etc. So many things, so many mean flow characteristics are there. So now there are some instability. Those instability analysis doesn't require information, these informations about different characteristics of the mean flow. Okay, but there are some instabilities which very critically require the information about the mean flow. What I mean to say, that stability or instability depends very much about the mean flow characteristics, dynamic characteristics, I mean to say. Mean flow dynamic characteristics means mean flow share, if it is there, if they are then horizontal or vertical, mean flow speed, etc., etc., all these things, acceleration, etc., all these things. Uh, those instability which does not depends on such information about the mean flow, they are known as static instability. Static instability. Static instability. Example of the static instability is very typical example is your Brunt Vaisala instability. Popularly, sometimes we call it partial instability. Thunderstorm is a typical example for the static instability. Its example is Brunt Vaisala instability. Is an example. Vaisala instability. And as I told you, that there are other instabilities which requires your these informations actually. They are called dynamic instability. That means such instability requires all the dynamical features of the mean flow. Okay, dynamic instability. Dynamic instability. There are examples are there. I am telling you. Instability. The examples, one is your inertial instability. Inertial instability. Then your barotropic instability. Barotropic instability. Then your another one is your baroclinic instability. Baroclinic instability. Baroclinic. Baroclinic instability. So this is one way of categorizing the instability. There you so this categorization I have done based on the mean flow characteristics. Similarly, now while defining what is called instability, we have mentioned that a perturbation is introduced in the mean flow. Now this perturbation may be looked as a small displacement. A small displacement. Displacement of an air parcel. Of an air parcel. Air parcel embedded in the mean flow. Embedded in the mean flow. Embedded in the mean flow. In the mean flow. This is one mean flow. This is one. In this way, a small displacement of an air parcel embedded in the mean flow. That means in the mean flow, I just take one small air parcel, but this is a small sample of the mean flow, and that part of the mean flow I just displace. I may displace it in the lateral direction, or that means meridional direction, or north south actually, and or I may displace it in the vertical direction also, and then I have to observe under what condition that displacement is continued. Displacement is continued. That means that air parcel never comes back to its original position, initial position, or under what condition it comes back. So accordingly, we say that it is stable or unstable. If it never comes, if it goes away from the initial position, then we will say it is unstable. And if it comes back, then we will say it is stable. So this is one way of looking a perturbation. There is another one way is also there. So suppose there is a mean flow. There is a mean flow is there. Suppose there is a mean flow. Mean flow is there, and in this mean flow, I just superimpose a small wave, just a small wave, small wave, and I will look under what condition this fellow with time is getting amplified, or under what condition it is getting dying. It is dying, and ultimately becomes state. Okay, so accordingly, so in this case, perturbation is looked like a small wave. It is a small amplitude wave embedded in the mean flow, and it is examined under what condition with time this wave perturbations is getting amplified or getting decays. Okay, so accordingly, there are two types of instability. One, we call it is a partial instability. Another one we call it a wave instability. So this is actually based on the nature of the perturbation. So here under partial instability, in the static instability, I am extremely, okay, that is fine. It is fine. In the partial instability, two things will be there, this one and this one. These two will come under partial instability. That means inertial instability and the Brunt-Vaisala instability, they comes under partial instability, and these two comes under wave instability. There is another one instability is also there, which is a mixture, which you cannot say it is a purely static instability or it is a purely dynamic instability. It is a mixture. Okay, that is one instability is there. That is called conditional instability of the second kind. Actually, you will find there is partial is also there, and at the same time dynamic is also. That we will discuss slowly. Okay, so this is about the classification. Okay, so now we will discuss about the partial instability or Brunt-Vaisala instability. We will discuss now. For discussing or to get to analyze the Brunt-Vaisala instability, first let us consider an air parcel. Let us consider an air parcel with volume say equal to sigma, and this air parcel being immersed in the ocean of air. So when it is immersed in the ocean of air, then it will definitely remove this much volume of air. Okay, so now if the density, let me write density of the air inside the parcel, density of air parcel let us write this is equal to rho P, and density of ambient air which is getting displaced due to this parcel, this is equal to rho A. Let me write rho A. Okay, rho A. So therefore what weight of the, we know that weight of the parcel which is acting downward, this will be is equal to density of the parcel into its volume into G. And another one thing also we know from Archimedes law that ambient air, this will be also trying to get occupying its lost region by putting a force in the opposite direction. Okay, well, so that force is equal to weight of the displaced ambient air. So the weight of the displaced ambient air, displaced ambient air displaced ambient air this will be is equal to rho into rho A into of course sigma and G. So and it will be acting upward. It is downward, it is upward. So now if I consider the vertical equation of motion of this air parcel, then we can see that this air parcel is being exerted upon by two forces in the opposite direction. One is this one, another one this one. So therefore vertical equation of motion, if I write, then it will look like this, that dw dt, this is equal to upward force minus downward force. That is equal to, it comes to be rho A minus rho P, into sigma into G divided by its mass. Its mass is equal to rho P into sigma. So it comes to be rho A minus rho P divided by rho P into G divided by G. dw dt is equal to this. So so therefore now if I apply the equation of state for the on the air or air, ambient air and the parcel air, and if I apply the kinematic boundary of kinematic boundary condition, means that means at the boundary pressure exerted by outside and pressure exerted by inside should be same. So kinematic boundary condition if I apply, then what I will get, that is density of the air, ambient air into temperature of the ambient air into R is equal to density of the parcel into temperature of the parcel into R. So therefore from here we can see that we can see that rho A minus rho P divided by rho P, it comes to be equal to component to dividend to root. If I apply, then it comes to be is equal to T parcel minus T ambient divided by T ambient. So we get this one. So therefore accordingly we get this one, T parcel minus T environment ambient divided by T ambient into G. So now so now what happened? Now suppose at Z is equal to Z0. Z is equal to, that means what I mean to say, suppose this is your surface. Initially the parcel was at the surface itself. Okay, so that time surface temperature and the parcel temperature, it was same. Okay, now the parcel is being pushed upward through some distance, say delta Z or something. Okay, so therefore this equation of motion what I have written, this is actually at the new position. So at the new position then what will happen? T at new position, let us say it is equal to Z0 plus delta Z. So if I apply here Taylor's series expansion, considering the ignoring the second other term, second order of smallness, considering the second order of smallness, then you will get, sorry, TP. You will get TP Z0 plus plus delta Z into del TP del Z, del TP del Z at Z is equal to Z0, of course. Z is equal to Z0 into delta Z. Delta Z, other terms we have ignored considering the second order of smallness. Okay, second order of smallness. Similarly, temperature, environmental temperature, ambient temperature at Z0 plus delta Z. This will be is equal to ambient temperature at Z0 plus delta Z into del TA del Z, del TA del Z at Z is equal to Z naught into delta Z, and other term we have ignored. So therefore from here we can see that temperature at Z naught plus delta Z minus temperature at ambient temperature at Z naught plus delta Z. This is coming to be, as I told you, that at Z is equal to Z0, since the parcel was at the surface, so therefore all the physical properties of the parcel is same as the physical properties of the air parcel itself. So at the temperature also same. So therefore this will be is equal to, these two will be cancelled. So this will be is equal to just del TP del Z, del TP del Z minus del TA del Z, del TA del Z at Z is equal to Z naught, Z is equal to Z naught into delta Z. Other term can ignore. So therefore our dW dt, this becomes is equal to, now we all know in the physics of the atmosphere, we have already read that there is a concept called lapse rate. Considering that actually lapse rate, so then we can see this is nothing but your that is your lapse rate of the air parcel. Now again you must have seen, you must have seen also, listen also during that physics of the atmosphere courses, that an air parcel actually it is a part of the air, of course, but it is isolated from the ambient air. There is no exchange of mass and energy between the environment outside the parcel and inside the air parcel. So that's why that process being followed by the air parcel, it is an adiabatic process. It is an adiabatic process. Now question is that if the parcel contains certain amount of water vapor, then we may call it a moist adiabatic, otherwise it is a dry adiabatic, but it is an adiabatic process. So and adiabatic, and also we know that rate of decrease of temperature with height, that is mathematically minus del T del J. This quantity we call it lapse rate, and we know all that with this quantity we denote by gamma. So therefore accordingly this one is the lapse rate of the ambient air. This is the lapse rate of the ambient air, and this is actually minus lapse rate of the parcel. So I may write it is the lapse rate of the parcel, and this is your lapse rate of the ambient air, ambient air, let me say environmental lapse rate we call E, and divided by what is there? Divided by T, divided by TA, correct? TA into delta Z, into delta Z. We get this one. So therefore, what we get? We get ultimately that dW dt is equal to minus G into T parcel, I am sorry, gamma P parcel minus gamma environment divided by TA into delta Z, okay. So now now what will now delta, this dW dt you cannot, we know very well this is nothing but your d2 dt2 of delta Z only, So now you can see this is a typical differential equation. Now if I say this quantity, suppose this quantity, if I put it n square, let us say this is equal to n square. So this is a typical differential equation, d2 dt2 of delta Z. Delta Z is nothing but vertical displacement plus n square into delta Z is equal to 0. And we know very well this equation gives a sine cosine solution. That means delta Z we may get as a solution like this, A into cos of nt plus B into sine of nt. We know very well sine of nt if n square is positive. We know very well. And also we know that it will have an exponential solution, that is delta Z. This will be is equal to A into e to the power nt plus B into e to the power minus nt. If n square less than 0. Now from here itself we can understand that, as we know that sine cosine can never be more than its magnitude will be always within 1 only. So therefore we can see that if this that means this is a stable only, this is a stable, but here there is a chance of instability because of this term. So therefore ultimately what criteria to what criteria we have reached? That the Brunt-Vaisala oscillation will be unstable if n squared is less than 0, and the Brunt-Vaisala oscillation will be stable if n squared is greater than 0. This n squared is known as, n is known as Brunt-Vaisala frequency. This is known as Brunt-Vaisala frequency. So therefore, for unstable case, what we require, that is n square must be less than 0. Now what is n square? Now let me go back. N square is equal to your gamma p minus gamma e. Gamma p parcel minus gamma environment into G by TA. It is less than 0. Now we know very well these are all positive. So that ultimately this condition implies gamma P is minus gamma E is less than 0. As I told that parcel follows an adiabatic lapse rate. It may be pseudo, it may be dry, whatever it may be. But what is the condition? Condition is environmental lapse rate is greater than the partial lapse rate. Now this partial lapse rate. Now this partial may be your this partial lapse rate may be dry adiabatic lapse rate, and this partial may be pseudo adiabatic, that is saturated adiabatic lapse rate. It may be saturated adiabatic lapse rate. So therefore there are two conditions. If it is so, then this will be implied. This will be implied because we all know that gamma D is greater than gamma S. And in that case, we will say it is a case of an absolute instability. Absolute instability. That's why I think Somenath sir can correct me. That's why, sir, sometimes dry thunderstorm, dry convection, actually it is more dangerous, I think. Absolute instability. Instability. If at all it happens, that means if your environment gets so heated that environmental lapse rate, so not only so heated, environmental temperature decreased at a very rapid rate, actually, because gamma D, we know more or less it is 10 degree Kelvin per kilometer. If the environmental cools with height more than 10 degree, okay, so that means surface is very much hot, very hot, very much hot. And but upper air is not that much hot, actually. Upper is relatively cooler. So in that case, there may be some cases where environmental lapse rate may exceed the dry adiabatic lapse rate. So in that case, it will be an absolute instability. Okay. And but suppose if this thing happens, then this is not implied that it will be, it is not implied. That means we have two conditions. One condition is when gamma is greater than gamma D. This is a case of absolute instability. But another one case is when gamma E is greater than gamma S, but not necessarily it is greater than gamma D, rather it is less than gamma D, then we call it an conditional instability. We actually, it is a conditional instability of first kind. So in this case, what happened? Positive air, moist air will be positively buoyant. Moist air will be positively buoyant, but dry air will be negatively buoyant in such atmosphere when your environmental lapse rate is within these two. And this is a case of conditional instability. Conditional instability. And conditional instability, very nice case is our thunderstorm development instability. Now question is, next thing is where from this energy supply, how it gets the energy. For that, actually, what happened? We have to integrate this equation. So now let me write down this equation again. That means dw dt is equal to minus G into temperature partial minus temperature environment, this one, divided by temperature of the ambient air into delta Z. So now what we do, both sides let me multiply by W. So this side of the W means d dt of delta Z here, d dt of delta Z. Okay, and now let us integrate it. Let us integrate both sides. Let us integrate from, suppose at t is equal to t naught, W is equal to W0, and at t is equal to something, that time W is equal to W only. And when T is equal to T naught, let us say this is Z is equal to J naught, and this is any Z. So therefore, what we get? We get W square by 2 minus W0 square by 2, 0 square by 2 is equal to is equal to you please pardon me. I think I made a mistake. Yeah, minus sign will not be there. Correct. This minus sign will not be there. So therefore it will get Z is equal to Z naught to Z G by TA G by TA TP minus TA. Okay, TP minus TA into no, as such, this integration is not required at all. This is not required. Without integration also we can do. That means W into dW dt. This, which is nothing but d dt of W square by 2. That is your vertical kinetic energy, which is required for the vertical development. This is equal to.
I think your whiteboard is not visible, Dr. Datta.
Why? Acha?
Are people able to see it? Dr. Rohini, can you see the whiteboard? Or it is stop sharing somehow?
No, it is so you are showing the your screen, your screen sharing, it is written. Or should I do one thing? Once I stop and then again share?
No, is everybody able to see your screen, Dr. Rohini? Are you able to see his screen, Dr. Aswin? Are you able to see the screen of Dr. Datta? I mean, the whiteboard where he's writing the equations. Are you able to see his whiteboard?
From when you are not getting shared, then
Just
I
now,
can.
just now. No, just now, a few minutes ago, just 1 minute ago.
We can see, we can see.
Sir, we can see, everyone can see.
Yes,
Oh,
yes.
yeah? No.
Okay, na?
The
Yes, sir.
whiteboard. Oh, yeah, maybe
Yeah,
some
yeah,
problem.
because even all the participants are replying, they all can see it.
Okay, fine.
Okay, fine. Maybe some problem on my side then.
Sir, your thing is okay now?
I'm just seeing you and others, but
So
not
then
your
what I
screen.
can do, first let me stop share, then again let me start sharing. Shall I do like this?
No, if everybody is able to see it, then it's fine. Only me, no
No,
problem.
you are not able to see now. Should I
It
do
will-
stop sharing and again sharing?
No, I think it will waste time because it is anyway there on the YouTube. If everybody is able to see it, then
Yeah,
it will
it's
be.
visible on the YouTube also, sir, because I
Okay.
have YouTube open.
Okay.
Yeah.
Then let's go ahead. No problem.
Okay,
I can watch on the YouTube live. No problem.
Okay. So therefore, we are having this dw dt. dw dt is equal to your g into t parcel minus t ambient divided by t ambient. dw dt is equal to this dw dt. So now let me see that one. Yeah, dw dt into g is there. Yeah, that's one. Into g. That's why this is your dw dt. So now both side actually I am multiplying w. So if I multiply w, So this side also I am multiplying W. So multiplying W means it is your dz dt. dz dt. Then we are integrating. Yeah. Then we are integrating. I made a mistake actually. Please pardon me. I am integrating it with respect to time. And when t is equal to initial time, suppose that time it is W naught, and at some arbitrary time, let us say it is W, and here here it will be say your Z naught, and here it is say arbitrary here Z. So therefore, from here what we are getting, that is W squared by 2 minus W naught square by 2 is equal to this integral Z naught to Z T by G by TA into TP minus TA dz. Okay, so now we all know very well, in the thermodynamics course we have seen that at LFC level of free convection, that vertical velocity is equal to 0, because at the LFC, why 0? Because at the LFC we know T parcel, because we know very well at the LFC T parcel is equal to T ambient. So therefore if I take, this is the initial condition, that is at LFC W is equal to 0. So then we can see very well that at any height, kinetic energy, that is W square by 2 at any height, this is equal to this quantity, that is Z at LFC to Z at any point divided by TP minus TA into dz. So now what is, now you can see very well, now we also know that so from here we can see that how long this will be equal to, it will be positive, how long it will be positive, this kinetic energy should be positive for vertical, because we know very well that for movement of any object in any direction, that object needs energy in that to move in that direction. So therefore for the vertical movement of the air parcel, it requires a positive energy, and this energy will be there unless and until this integral is positive, isn't it? And we know very well these are all positive, so this integral will be positive unless and until the parcel temperature is more than the environmental temperature, that we know very well. And if you remember that that is T5 diagram portion of your atmospheric physics course, there you must have seen that at the LFC, parcel temperature is more than the environment, parcel temperature is equal to the environmental temperature or ambient air temperature. After that, parcel temperature is greater than the ambient temperature, and then falling at some point at the upper air, at some point again parcel temperature becomes equal to the environmental temperature. That level also we know, this is known as level of neutral buoyancy or equivalent level, that also you know very well, level of neutral buoyancy. And after that ambient temperature becomes greater than the parcel temperature. Okay, so therefore we are ensured up to which layer, in which layer this will be positive. That means from Z LFC to Z level of neutral buoyancy, up to this is positive only. And this quantity we all know very well, you must have read, this is known as convective available potential energy. So therefore what we have learned from here, that the Brunt-Vaisala oscillation, if it becomes unstable, how it becomes? By drawing the convective available potential energy from the ambient air. And we stop here today. Thank you, sir. I hope today I could finish in time.
Yes, sir. Thank you. Before we go to the question answers, I request all the participants to write their questions in the Q&A box. Before we go, we will take have photo session. So I request Tyagi sir, Ashwin to please switch on their camera. It's only V4. Tyagi sir. Yeah. So Ashwin, can you take pictures?
Yeah.
Actually, Tyagi sir is muted. He wants to speaking, but he's muted.
Sir, you want to say something, Tyagi sir?
You're speaking.
You are muted, sir. You are muted. Yeah.
Along with the instability there in the lecture, there was a severe thunderstorm in Delhi last half an hour.
Oh,
Wow. Okay, so this question answer session was to be moderated by Mrunal Naik, but she had some urgent meeting. So I think there is one question. I will go ahead with that. Thank you, sir. This question is given by Dr. Ira Upadhyay. Thank you, sir, for your insightful lecture. My question is related to application in air quality study. How can hydrodynamic instabilities influence the creation and breakdown of temperature inversions that trap air pollutants near the ground?
no, yeah, very good question. Thank you for the question. Now, first of all, we have learned from here one thing. That is, if I can measure just one quantity, Brunt Vaisala frequency square, n square, and just monitor its sign, positive or negative. So now question is, suppose for air quality, because we all know very well that air quality is due to air pollution. If the air pollution disperses from my place, I don't have any problem. My problem is there if the air pollution remains stagnant in my place. Okay, so now question is, if the low level, if the atmosphere is unstable, then in that case what happen due to vertical motion, if there is any low level, any air pollution is there, it will just move away. It will just move away. But if it is not so, if it is stable, then in that case it will be that is air pollution will remain there, and as a result of which it will create create damage to the air quality. So in this way, that is this particular instability study can be useful for the air quality study. That means just we have to find out the Brunt Vaisala frequency at the lower level. Lower level means up to 150 850 HP. It is more than sufficient. It can be found out actually. It can be found out. A small program from temperature, pressure, etc. We have to find out potential temperature. Then it is G by theta, D theta, dz only. But that's all. And if it is positive, that means it is stable. That means it is going to hamper your air quality. And if it is negative, so that means it cannot remain stagnant at the lower level. So that's why now winter season actually this inversion is there. When inversion means low level is stable actually. Low level stable means actually this one actually, that is n square. N square is positive. I hope I have been able to answer her question at least partially.
Yeah, she replied back saying thank you. So maybe she has got the answer. Anyone else wants to type the questions, or we can wait? So there was one question actually. Instability is slightly difficult, sir.
No, because I want to make it simple.
Yeah, you made it.
But it is very interesting. Instability is very interesting topic.
There is one question by Josan. Sir,
Huh.
vertical temperature gradient is necessary for instability?
Of course. But it is, of course, because if you see, again, I am telling you, this entire instability story is it's standing on one quantity, that is Brunt Vaisala frequency. Now, this Brunt Vaisala frequency, what is the expression? If you see, that is your, it requires two things. One is your that is your lapse rate of the environment. What is lapse? And another one is lapse rate of the parcel, air parcel. So now, if your air is completely dry, if which you can find out actually, if your if the relative humidity of the air is too less, then in that case, your that is partial lapse rate will be almost 10 degree Kelvin per kilometer. And but for your environmental lapse rate, you require vertical temperature gradient, na? That is dt dz. It is required. It is required. You have to calculate this one. You have to calculate this one and and then you have to compare it that that whether it is greater than the partial lapse rate or not. That is either it is dry adiabatic lapse rate or it is greater than the saturated adiabatic lapse rate. So temperature gradient is very much important. You have to calculate actually. Without that, you cannot calculate. I hope I have been able to answer his question partially, at least. Professor Das, I think you are muted, sir.
Oh, I see. Yeah, Dr. Rohini also is mute. We can't
Oh,
hear you.
sorry. Oh, sorry. Yes.
Yeah.
There is another question by HGPA Ratnavira.
Okay.
In equatorial wave theory, is the square of the frequency equals to GHK raised to 2? If so, could you elaborate on its significance?
But I am not able to understand.
Sir, he has asked, in equatorial wave theory,
Huh.
is the square of the frequency equals to GH into K raised to 2?
Maybe it is related to the
Okay,
last.
new. Acha, that is a
He has
different
written
topic.
K. Huh.
Yeah.
So
Acha.
if
No,
so, could you elaborate on its significance?
No, actually, what happened in the equatorial wave theory, whatever you're telling, that is nu is equal to hk. Nu is equal to
Yeah, he has written GHK raised to 2.
K square.
K square.
Nu into nu is equal to k square into h, like that. Now what? Now nu square.
G into h into k square.
So actually, it is the dispersion relationship. It is the dispersion relationship for that particular wave. I think it is gravity wave, most probably. GH. I think it is external gravity wave only. GHK, na madam?
Yes, sir.
Under root GH into K. Under root.
Yeah, maybe he couldn't write.
Nu is equal to under root GH into K. It is significance means for every wave, there is a dispersion relation. Dispersion relation is nothing but it is the relation, because we know very well that for every wave there is some frequency, there is some wavelength, etc. is there, and just 1 by wavelength is equal to your, we know what is called that is sorry, not 1 by wavelength, 2 pi by wavelength is nothing but your wave number, that also we know. So now any relation between the frequency and the wave number, this is called the dispersion relationship. So now this dispersion relationship is very important, because if the dispersion relationship is linear, then we will behave differently. If the non-linear, then for example, in this case, you are telling nu is equal to under root GH into small k. That means frequency is a linear function of wave number. So which ensured that this wave is a non-dispersive wave. Means this wave, for this wave, that transport of momentum and transport of energy is taking place at the same speed. So for such wave, actually leaking of energy's chance is less or chance is 0. But had it been under root gh into k square, then it would become a non-dispersive wave, dispersive wave. In that case, we would have got, which we have seen in case of Rossby wave, that that is your, what is called your, that is your rate of transport of energy differs from the rate of transport of momentum. So in that case, actually both are moving in a with a different speed, so there is a chance of energy transport, that leaking of the energy from one to other.
Thank you, sir.
Mm.
There is another question by Krishna Priya M. Sir, can you explain why thunderstorm is considered an example of static instability?
Because in the thunderstorm, now in case of the thunderstorm, in a thunderstorm actually, we just want to know, we just require the information of the temperature and the vertical distribution of the temperature, and there was moisture. We don't require the information about the what is the wind shear and all this thing, etc. We don't require actually, because if you remember the thunderstorm development criteria, whatever criteria is there, so there actually this stability information is only required. That is a static stability information. You remember in the thunderstorm there is one criteria, there should be low level instability. Whatever this low level instability refers here, this is nothing but this instability only. And this instability analysis, you can see we have never used the any information about u or v, or we have never information about any grad u or grad v or del u del z or del v del z. We have never used, isn't it? Directly, rather I should say explicitly, they are not used. Explicitly, implicitly it may be there. For example, implicitly how? What I am telling you. Suppose if there is a very strong vertical shear, if there is a very strong vertical shear, okay, then in that case, this should I now can I start share just
Yeah, yes, sir, yes.
say whatever is there, but suppose there is a very strong vertical shear, low level is this much and upper level is very strong vertical shear. So now this strong vertical shear, what happened, it also drives a forced convection like this. Actually this is also forced convection. This sometimes helps actually. Suppose there is a thunderstorm, you consider two cases. In one case, there is a very strong vertical shear is there. In another one case, strong vertical shear is not there. Very weak vertical shear is there. You will see the change in the difference in the intensity of the thunderstorm. Is it okay?
Yes.
So actually, whatever convection, whatever I discuss in the stability, this is a free convection. Level of free convection is there. But along with that, if this vertical wind shear, all these things is there, forced convection will also add in, and which helps in intensification of a thunderstorm development.
Thank you, sir. So
Have I hope.
yeah, she has replied back. Thank you for the clarification. Yes. So now there are no more questions. So maybe we can wait till a vote of thanks if there are any more.
Thank you.
Oh, one more has come.
Yeah.
So
No,
there is a question from Priyanka Parapolhe. If Brunt Vaisala frequency is positive at upper troposphere over Eurasian region, then how it can affect weather in that region?
Actually, this Brunt Vaisala frequency positive, negative, while discussing, I have never mentioned that it is any latitude specific. It is not so. Actually, this Brunt Vaisala frequency mainly determines basically initiation of a convection or not, you know. So now, wherever you are, if the Brunt Vaisala frequency is positive, it implies the atmosphere over that place is stable. So therefore, no convective instability cannot take place. That's all. Whether whatever be the latitudinal belt.
Okay, sir.
Have
So,
I?
yeah, yes, she. So no more questions yet. We will go to vote of thanks. I request Mr. Ashwin Zadav from SPPU to please conduct vote of thanks.
Thank you, madam. Thank you, sir, for a very enlightening lecture. I'll share my screen. So on behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 17th lecture in our weekly online lecture series on atmospheric dynamics and applications to climate sciences. So we are especially grateful to Professor Tohinda Rashid, Department of Meteorology, University of Dhaka, Bangladesh, for her warm welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Dr. Somenath Dutta from IMD Kolkata, for delivering an enlightening lecture on definition and categorization of hydrodynamic instability, Brunt Vaisala instability. I would also like to acknowledge Dr. Onivar for moderating the session and for efficiently managing the question answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members. A special thanks to all the participants and attendees who joined us from across the globe and to the dedicated team members at Savitribai Phule University for their invaluable role in organizing this lecture. Thank you. Thank you all.
Thank you, Ashwin. So no more questions. Thank
Yeah.
you. Yeah.
In fact, with regard to the last question that if the Brunt Vaisala frequency is positive at upper troposphere
Over
or
Eurasian.
Eurasian region. Now the thing is that regardless of the upper or lower troposphere or regardless of the whether it is a Eurasian or anywhere, once the Brunt Vaisala frequency, as explained by Dr. Datta, once it is positive, that means it is stable, wherever it is, right? So basically, it is just telling you whether the atmosphere is stable or unstable, depending upon the sign of the Vaisala frequency, right? This stability topic is very important and very interesting topic. There's so many kinds of instability in the atmosphere, and all that weather that you see is somewhere or the other related to some kind of instability. Now, the next two lectures also will be covered by Dr. Dutta on different types of instability, like the inertial instability, the barotropic instability, the baroclinic instability, and there are many more which probably will not be able to cover in these lectures, like symmetric instability. You might not have heard about the symmetric instability. There are symmetric instability, especially in the mid latitude, which cause the slant-wise convection.
Yes, sir. Yes, yes.
Right. And also, you might have heard about the conditional instability of the second kind.
Second kind.
Right. So, especially for the development of the tropical cyclone, this CISC mechanism is very important. So, if it is a conditional instability of the second kind, then you should be curious to know what is the conditional instability of the first kind in that case. And that's what Dr. Datta has explained today. The first kind of instability. Also, the instability, there are numerical instability, especially when integrating the numerical models in the NWP, there are numerical instability. And we get numerical nightmares.
Yes.
Because of the numerical instability, the model bumps, the model blows up because of the numerical instability. And you must have heard about the CFL criteria, the Quran,
Yeah.
and Lewis conditions. So there are many kinds of instability, not only in the atmosphere, but also in the numerical equations
Ah.
that leads to so many kinds of nightmares for the scientists. So you should be familiar and aware about these things.
This is my favorite topic, sir. This
Oh yeah, of course
hydrodynamic
it is.
instability.
Very, very
Yes.
interesting topic. Very, very interesting topic. I hope the participants are carefully listening to it. Only 45 are there now. But anyway, it will be available on the YouTube. The entire lectures will be
Yeah.
available.
I will, before closing down the YouTube link, I would like to give the statistics. So around 101 participants have registered their attendance, out of which 90 participants have rated it as excellent and very good. So,
Thank you.
yes, sir. They are enjoying the board lectures. I mean, the blackboard lectures
Yes.
again. So,
Let it be useful by them actually, because
yes, sir.
we are old person. Excellent may not be required.
Dr. Dutta,
Excellent.
old is gold. Old is always
Gold
gold.
is always gold.
No, no, that's why excellent may not be required. Main thing is it should be useful by them as such.
Yeah, of course it is useful. But people can learn more easily in a better way when you explain on the board.
Yes, sir.
Slowly.
Achha, another one thing I have forgotten. I will give some what is called material actually. Whatever my lectures, I should have
Yes.
given some material. I have that is in the PDF format. It is there. I
Okay, sir.
prepared. I will give in the
So,
same mail. Can I send? What?
yes, the
I
same.
will send. I will send.
Whenever you send, we will share it from university.
Okay. I will give. I will give.
And sir, you also have some questions, MCQs.
Question
Yeah.
also we have to give.
So
I
on
will
each
give.
of your lecture 5 or 6, so that we can have.
I have to give. I will give.
So I'll first stop the live stream.
Okay.